Today we start on important topics related to nonlinear space. Also discuss in previous class so many examples, so many theorems, and also Minkowski inequality, Holder's inequality, so many inequalities. Today I also discuss from example of normed linear spaces. Okay, we start from one example and going to further one. Also right here now. Just write this one. Let x equal to k to the power n. Or k with some field. Okay. Then k to the power n. The space of all n tuple of elements of k. The space of all n tuples of k or n tuples of element of k. Okay, that means all elements are belong to k, and obviously these are in the form of n tuples. Okay, then we're also going to here this one, define one norm, define norm infinity. Okay, define norm infinity from x to r plus union 0. Okay, by norm x infinity equal to maximum of this one, norm x1, norm x2, dot 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 norm xn. Okay, then where x equal to where x equal to x1 x2 dot 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 xn. In this way this n tuple, okay, belongs to this k to the x equal to k to the power n. Then what happened? Then obviously x this norm infinity be a normed space or normed linear space. Okay, we have to prove it. We have to prove this problem. We have to prove this problem. This one is easy problem. We have to prove it. Okay, then what we do? We start from proof first portion. Just we known about that some non-negativity condition. We known about, we marked it in n1 and write it this one, norm x greater than equal to 0. Obviously any norm is greater than equal to 0. Okay, for all x belongs to x. And then again we have this one is by definition, we write it by definition of norm. Okay, and then we check it, norm x infinity equal to 0 implies what? Implies maximum of this entities mod x1 x2 dot 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 x3 dot 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 xn equal to 0. This implies what? This implies norm of x1 norm of x2 equal dot 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 norm of xn equal to 0. Okay, if greater than 0 then this maximum is greater, and less than 0 is not possible, so all are 0. Then what happened? Norm is 0 means each entity is 0. I understand. Then this implies what? X equal to 0 0 dot 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 0 equal to big 0 belongs to k to the power n. I understand. Not a problem at all, I think. Okay, so this was this happened. Then what happened? Then also that means we're getting this result. Which result? we erase now this, we erase this portion, and obviously first result we get norm x infinity greater than equal to 0 and norm x is equal to 0 implies that x equal to 0. Now we're going to second portion. Norm of alpha x equal to what? Norm of alpha x equal to this one infinity equal to what? Equal to, we know about that, this one maximum of, okay, alpha x equal to what? Alpha x1 mod of alpha x2 dot 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 mod of alpha xn. Why? Because where alpha x equal to alpha x1 alpha x2 dot 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 alpha xn belongs to k to the power n. Okay, too easy. Now we just define this one, and now going to be calculate. Here mod is outside, mod alpha mod x2 dot 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 mod alpha mod xn. Then what happened? Mod alpha maximum of this one. Okay, then what happened? Then this one equal to mod alpha norm x infinity. So what we get? We get the second conditions are satisfied. Okay, that means we get this one norm of alpha x infinity equal to mod alpha norm x infinity. Not a problem at all. Now we're going to this third triangle inequality. Okay, what do we have to prove? We have to prove, we write it fast. We have to prove that norm of x plus y infinity less than equal to norm x infinity norm y infinity. We have to prove this one. Okay, what we do? We do so simply, just write it now. X plus y infinity equal to maximum of what? x1 plus y1 x2 plus y2 dot 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 xn plus yn. Okay, this equal to what? This less than equal to maximum of mod of x1 plus mod of y1. Here mod of x2 plus mod of y2 dot 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 mod of xn plus mod of y. Okay, then what happened? We erase our portion and going to further discussion of that. Okay, then we get this one less than equal to maximum of this dot 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 this plus maximum of this one. I understand this one is obviously greater or equal to maybe. Okay, then this one equal to not equal to this one is mod x infinity mod y infinity. So what happened? We get this our required result. Norm of x plus y infinity less than equal to norm x infinity plus norm y infinity. I understand this was is done. Not a problem at all. Okay, then what we get? We get our required result. We write it now. Thus norm infinity satisfied all the conditions of norm. Okay, then therefore x norm infinity be a norm space. Now also prove this example. Obviously if we do it for LP space, Okay, this one is just kn, x equal to k to the power n. Okay, so to easily we done it. Obviously in L infinity this one is solvable, and in LP also solvable. L infinity also norm space, but we are not interested now doing this. We also write now LP. Okay, LP be a norm space, we also proved now. So we write this statement first. This one LP whose type of set, that means x equal to xn. Okay, xn belongs to k such that summation of n equal to 1 to infinity norm of xn whole to the power p less than plus infinity. That means p is summable. Okay, finitely p summable sequence, collection of finitely p summable finite p summable sequence. Okay, then this one is LP set. Okay, now we're going to define norm xp. Define norm xp equal to, okay, equal to what? N equal to 1 to infinity norm of xn whole to the power p whole to the power 1 by p. Okay, x equal to xn belongs to LP. Understand? Then what we have to prove? Then we have to prove that LP be a norm space. We have to prove this one. Same thing, this norm P satisfies all conditions of norm, then this one is done. Okay, how we do it? We proceed. Now write proof first, and going to be first conditions. Which conditions? We know about that by definition of norm infinity, norm x infinity greater than equal to 0 for all x belongs to f. Okay, that means norm infinity equal to what? Norm infinity, not here, norm xp. Norm xp equal to what? Norm xp equal to summation n equal to 1 to infinity norm of xn whole to the power p whole to the power 1 by p. That means all positive terms are obviously pth power. Okay, then this term summation whole to the power 1 by p. Okay, then this one are obviously, that means some positive term power, that means always positive, and this sum is always positive, or this whole to the power 1 by p gives a positive value. I will understand. So this one is always positive. Otherwise, if all xn are 0, then this one be 0. So always greater than equal to 0. Okay, by definition. And again we talk about it. Here x belongs to LP. Norm of xp equal to 0 implies what? Implies this one equal to 0, n equal to 1 to infinity norm xp whole to the power 1 by p equal to 0. This one implies what? This one implies n equal to 1 to infinity norm of xn whole to the power p equal to 0. This one implies what? This one implies xn equal to 0 for all n belongs to natural number. This one implies what? This one implies x equal to 0. Okay, and obviously we not do it in previous that means previous example, but this one is done. If x equal to 0, then obviously norm xp is 0. Okay, we not do it in previous example, but this one is obviously needed here. Okay, just this one. If x equal to 0, then norm xp is 0. This one is a, that means generally this one is fault. Okay, but if this one is obviously, that means doing here because this one needed. Now we're going to further proceed here. This condition of norm, which condition? Norm if x belongs to LP and alpha belongs to K, then norm of alpha xp equal to what? Summation n equal to 1 to infinity mod of alpha xn whole to the power p whole to the power 1 by p. Okay, this one equal to what? We erase our portion and going to further discussion of that. Okay, that means this equal to what? This equal to obviously summation n equal to 1 to infinity norm of alpha to the power p norm of xn whole to the power p whole to the power 1 by p. This equal to what? This one equal to alpha to the power p summation n equal to 1 to infinity mod of xn whole to the power p whole to the power 1 by p. This equal to what? This equal to norm of alpha summation n equal to 1 to infinity mod of xn whole to the power p whole to the power 1 by p. Okay, this equal to what? This equal to obviously mod of alpha norm of xp. Then what we get? We get this second conditions are satisfied. Okay, for all x belongs to LP. Next we also going to further third condition. Okay, if this third condition is satisfied, then we also do it. But if we do it, that means write this one, let xy belongs to LP. Okay, then what happened? Then x plus y p, x plus y norm p equal to summation n equal to 1 to infinity norm mod of xn plus yn whole to the power p whole to the power 1 by p. Okay, this one we obviously known about that Minkowski inequality, and using this Minkowski inequality here, if we want to prove it, then this one is better. Okay, so how we prove it? Okay, also again we write it now. This one, that means again we write properly. We write it this one, n equal to 1 to infinity norm of xn whole to the power p whole to the power 1 by p, and norm of yp whole to the power n equal to 1 to infinity mod of yn whole to the power p 1 by p. Then what we have to do? We have to do write it now. We have to prove that what? Norm of x plus y whole to the power norm p less than norm x p norm y p. This one we have to prove it. Then what we do? We do in this way, n equal to 1 to infinity norm of x n plus y n whole to the power p equal to what? Equal to, in this way, this one equal to n equal to 1 to infinity norm of xn plus yn whole to the power norm of xn plus yn whole to the power p minus 1. Okay, then we erase our portion and going to further discussion of that. We write now less than equal to summation n equal to 1 to infinity mod of xn, here xn plus yn whole to the power p minus 1 plus n equal to 1 to infinity yn whole xn plus yn whole to the power p minus 1. we also used Holder's inequality. That means if you not understand, then again prove Holder's inequality. But this one is not needed now. We directly we write this Holder's inequality. This one, okay. This one whole to the power p 1 by p, and this one n equal to 1 to infinity xn plus yn whole to the power p minus 1 into q whole to the power 1 by q, where p 1 by p plus 1 by q equal to 1. Okay, then in this way here n equal to 1 to infinity yn whole to the power p 1 by p and summation n equal to 1 to infinity norm of x and y n whole to the power p minus 1 into q whole to the power 1 by q, where 1 by p 1 by q equal to 1. Okay, then what happened? Then but here this one is by Holder's inequality, we used it. Okay, then what happened? Then this one less than equal to this one n equal to 1 to infinity norm of x n whole to the power p 1 by p, and here p minus plus this one n equal to 1 to infinity norm of yn whole to the power p 1 by p whole, then common this one n equal to 1 to infinity norm of xn plus yn whole to the power p minus 1 into q whole to the power 1 by q. Now p minus 1 from here 1 by p plus 1 by q equal to 1, then 1 by q equal to 1 by p, then p minus 1, then this implies p minus 1 into q equal to p. Okay, so what we get? We get from here this one n equal to 1 to infinity norm of xn whole to the power p 1 by p plus n equal to 1 to infinity norm of yn whole to the power p 1 by p. Then what happened? Remaining one is this one n equal to 1 to infinity norm of xn plus yn whole to the power p 1 by q. Then again we erase our portion and going to further discussion of that. We also going to this one, that means summation n equal to 1 to infinity norm of xn plus yn whole to the power p whole to the power 1 minus here 1 by q. Okay, less than equal to this one summation n equal to 1 to infinity norm of xn whole to the power p whole to the power 1 by p plus n equal to 1 to infinity norm of yn whole to the power p whole to the power 1 by p. This one equal to n equal to 1 to infinity norm of xn plus yn whole to the power p whole to the power 1 by p less than equal to this one. This implies that norm of x plus y whole p less than equal to norm of xp plus norm of y. Okay, that means we prove this portion, this triangle inequality using, that means if always we write it by Minkowski inequality, but we also prove it now. Okay, again we also prove this Holder inequality by use this, that means Young's inequality. Okay, and also prove this Young's inequality by using this derivative. okay, or property of derivative. So this one is not needed here, just we write it this: norm P satisfies all these conditions of norm, all the conditions of norm, then this x equal to LP and norm P VA norm space. Okay, then we also done it. Okay, now we're also going to discussion about another one, some function space, and obviously see about that. Okay, that means some linear space of all real valued functions where f can be continuous. Okay, that means k derivative of f be continuous in this space. We also denote it c to the power k ab to r. Okay, then we also discuss this space. And also discuss Holders and Minkowski inequality in CAB. Okay, so today we also stop here.